Myself, Dr. Shemi PM, Associate Professor, Department of Electronics, MES College, Marampally.
Hi everyone, welcome to my session on noise and communication systems. In this session, I'll be giving an introduction on noise, sources of noise, the different classification of noise, noise evaluation parameters, signal to noise ratio, noise figure, and noise temperature. Noise, as you all know, is an unwanted signal that tend to disturb the transmission and processing of signals in communication system and over which we have no control. The different sources of noise includes channel. Channel is the main source of noise in communication system. The transmitter or receiver circuits may also induce noise in the system. Claude E. Shannon conceptualized the communication theory model in the late 1940s. Figure shows a block diagram of a communication system. We have the transmitter part, we have the receiver part, and a channel in between. The transmission side consists of information source and the modulator. The modulator signal is passed through the channel, and at the receiving side we have the demodulator and the destination. So here we can see that the source of noise come mainly in the channel part. The transistor or receiver circuit may also noise in the system. The effects of noise include the noise will definitely degrade the system for performance for both analog and digital system. The noise affects the sensitivity of receivers. Sensitivity is defined as the minimum amount of input signal necessary to obtain the specified output quality output. Hence, it degrades the output quality of the output signal received at the receiver. It also reduces the efficiency of the communication system. So as you all know, noise are unwanted signals that interferes with the original message signal and corrupts the parameters of the message signal. These unwanted signals arise from a variety of sources which may be considered in one of the two main categories: external noise source, which appears external to the system. Internal noise source are mainly internal to the communication system. So the types of noise are of two: external noise and internal noise. The external noise is again classified into two types: natural and man-made noise. Naturally occurring random noise appears due to either natural phenomenon or atmospheric actions like solar flares, radiation in space, electronic storms, etc. The second category, interference, usually form from a human source or man-made noise. It arises from other communication systems like crosstalk, 50 Hz supply, hum and harmonics, switch mode power supplies, SMPS, thyristor circuits, ignition motors, etc. Man-made noise is a type of extrinsic noise and is also known as industrial noise. These are basically the electrical noise that gets produced by the wear and tear of the circuit being used. The source of man-made noise is electric motors, high current circuits, fluorescent lights, switch gears, etc. So when these machines operate, arc discharge takes place and this discharge generates no signals in the communication system. The frequency of man-made noise lies in between 1 MHz to 600 MHz. The sources of man-made noise include high voltage power line discharges, electric motor noise generated by armature and switching takes place in the motor, ignition noise in automobiles and aircraft, at telephone exchanges where switching takes place as a source of impulsive noise. The second category is natural noise. The natural occurring external noise sources include atmospheric disturbance, examples electric storms, lightning, ionospheric effect, etc. So-called the sky noise or cosmic noise, which includes noise from galaxy, solar noise, and hot spot due to oxygen and water vapor resonance in the Earth's atmosphere. Figure shows an idea on different noise, temperature versus frequency graph. Internal noise or fundamental noise that gets generated by the electronic equipment involved in the system itself. They are called so because these are nothing but an integral part of the system. Obviously, they will generate once the system is taking into place. Proper designing of the communication system can reduce this internal noise or noise due to internal sources. Internal noise is further classified into thermal noise or white noise or Johnson noise, short noise, and transit time noise. Noise or Johnson noise or white noise is a noise generated in any resistance due to the random motion of electrons. This type of noise is generated in all resistances, example resistor, semiconductor, resistance of a resonance circuit, etc. Experimental results by Johnson and theoretical studies by Nyquist give the mean square noise voltage as V square is equal to 4 kTBR, where K is a Boltzmann constant, which is having a value of 1.38 into 10 power minus 23 joules per Kelvin. T is the absolute temperature in Kelvin. That is, in Kelvin, you have to add 273 to the degree Celsius temperature. B is the noise bandwidth measured in hertz, and R is the resistance measured in ohms. The low relating noise power Pn to the temperature and bandwidth is given by Pn is equal to kTb watts. Thermal noise is often referred to as white noise because it has a uniform spectral density. The figure shows the uniform noise power spectral density of thermal noise, which is constant of P. Coming to the second category, short noise is produced by the random arrival of electrons or holes at the output element, at the plate in a tube, or at the collector or drain in a transistor. It's also produced by the random movement of electrons or holes across a p-n junction. So for p-n junction, the mean square short noise current is given by IN square is equal to 2 into IDC plus 2 I naught QEB amp square, where IDC is the direct current at the PN junction measured in amperes. I naught is the reverse saturation current measured in amperes. QE is the charge of the electron, just having a value 1.6 into 10 raised to minus 19 coulombs. B is the effective noise bandwidth measured in hertz. Short noise is also found to have a uniform spectral density, as in the case of thermal noise. Transit time noise is another kind of noise that occurs in transistors. It's also known as high frequency noise. It arises when the charge carriers require comparatively more time to travel from one end to another within the conductor, and this effect is normally known as transit time effect. For low frequency applications, this effect is avoidable, but for high frequency applications, the effect is unavoidable. So due to this transit time effect, random noise gets generated inside the device and is known as the transit time noise. Other noises include low frequency or flicker noise, excess resistor noise, burst noise, or popcorn noise. Active devices, integrated circuits, diodes, transistors, etc. also exhibits a low frequency noise which is frequency dependent. Excess resistance or resistor noise, the resistors generate an additional frequency dependent noise referred to as excess noise. Hence, noise in resistors is a combination of thermal noise and excess noise. At low frequencies, excess noise dominates, while at high frequencies, thermal noise dominates. The next category is burst noise or popcorn noise. Some semiconductors, it is exhibited or it is produced in some semiconductors. They also produce this noise with a spectral density which is proportional to 1 by f square. That is inverse proportional to reciprocal of frequency, square of the reciprocal of the frequency. Coming to the general note on the noise for frequency, you can see the noise versus log of frequency graph. For frequencies below a few kilohertz, low frequency system, flicker and popcorn noise are the most significant, but these may be ignored at higher frequencies where white noise predominates. Now coming to noise evaluation parameters, signal to noise ratio SNR is defined as a ratio of signal power to noise power, and it is expressed as S by N is equal to Vs by Vn the whole square, where Vs is a signal voltage and Vn is a noise voltage. The signal to noise ratio is normally expressed in decibels. SNR in dB is given by 10 log 10 SNR ratio. Noise figure is defined as, it is denoted by F if is defined as a ratio of the signal to noise ratio at the input to the signal to noise ratio at the output of the system. The noise figure is also called as a noise factor. The amount of noise, it indicates that the amount of noise added by the network is embodied in the noise factor F, which is defined by F is equal to SNR at the input by SNR at the output. F equals 1 for the case of noiseless network, and is in general F is greater than 1. The noise figure is expressed in decibels. The noise figure F in dB is given by 10 log 10 F, where F is greater than 0 dB. Noise figure or noise factor is a measure of how much a network degrades the SNR, input SNR. The lower the value of F, the better the network. And coming to the noise temperature Tn is a way to express noise of a system in terms of an equivalent temperature. It is not the physical temperature of a system; it's a theoretical value that defines an equivalent temperature required to produce a specific amount of noise power in that system. It is defined as the equivalent temperature of the noise power per unit bandwidth of an active or passive system at any given frequency. The noise temperature is expressed as Tn is equal to Pn divided by B into K, where Tn is a noise temperature, Pn is a noise power, B is a noise bandwidth, receiver bandwidth measured in hertz, and K is the Boltzmann's constant, which is having a value of 1.38 into 10 power minus 23 joules per Kelvin. Noise temperature can also be defined in terms of noise factor as Tn is equal to F minus 1 into T naught, where F is a noise factor and T naught is the absolute temperature of the environment and is 290 Kelvin. Thank you.